Starting off here with a question about enthalpy of formation and writing out the equation for it. Now, quite a number of things that you need to slot into place to get this mark. You have to know that iron 3 oxide is Fe2O3, and you also need to know that it's formed in its standard state at standard temperature and pressure, so it's solid. We know that it's going to be Fe2O3 because the 3 Roman numerals tells us the iron is +3. We know that oxygen has a -2 charge as an ion because it's in group 6. Now we also need to know that the enthalpy of formation is the formation of 1 mole of a compound from its elements. So that's what we've got there, Fe and O2, remembering that O2 is diatomic. And they're also in their standard states, so that's solid Fe and gaseous O2. Now what's left is the balancing, and that's 2 Fe, 3/2 O2, and 1 mole of Fe2O3. And again, it's worth just reinforcing here, if you'd balanced this up to have more than 1 mole of Fe2O3, it would no longer be the standard enthalpy of formation. When it then comes to the calculation that follows and building the cycle, we have been given enthalpy of formation data for carbon monoxide, for iron oxide. We haven't been given it for carbon dioxide, and we haven't been given it for iron. But I'm going to start by building up the cycle and drawing it out. And we know that the enthalpy change is -19 as shown on here. But I've also added the elements which are going to be used to make up the compounds. Again, we're looking at standard enthalpy of formation data. From here, I can then identify where there are 2 different routes, and I've highlighted those in different colours. Hess's law tells us that the overall energy change is the same whichever route is taken. So both of those routes will add up to the same value. I can then start to put some figures in. I know that the enthalpy of formation of Fe2O3 is -822, and I know the enthalpy of formation of carbon monoxide is -111, but I've got 3 moles of that, so I multiply that value by 3. I also know my enthalpy of formation of Fe, because the Fe is the element in its standard state at standard temperature and pressure. The enthalpy of formation of it is 0. As a different exam question, if you were asked why it's 0, it's really simple. It's by definition. Now we want to know the enthalpy of formation of carbon dioxide. So because we're making 3 moles of it, we can say that the remaining value to go in there is 3x. Now I can then put those figures in to an expression, -822 take away 19 plus the 3 times -111 is equal to 3x. So 3x is therefore equal to -1174. Now I can then divide that 1174 by 3 and I get my enthalpy change of -391 kilojoules per mole. And here we have another Hess cycle, but not one that you'd be familiar with necessarily. More commonly, you'll have enthalpy of formation data provided, sometimes enthalpy of combustion data provided. But here we've actually got bond dissociation enthalpies given. So let's start with the cycle itself. I know from the table that N2 plus 3H2 going to 2NH3 is -92. I can also look at what would happen if I break apart an N2 and break apart 3H2s. I would end up with 2N and 6H. The plus 944 is what's needed to break apart the N2 into the 2 N's. And I would need 3 of the 4 3,6s to break 3H2 into 6H. Now I want to know what the bond enthalpy for an NH is. I've got 6 NH bonds in 2 NH3s. So I'm going to put 6x in there. And I've then got all of the figures that I can put in, and I've colour coded them based on the colours of the arrows for the 2 routes. So 2252 is -92 plus 6x. A little bit more rearranging. 2344 is 6x, and then nice and simple to finish off, x is 391 kilojoules per mole. Then we need to think about a reason why the bond enthalpy we calculated is different from the mean bond enthalpy. Now, this is a very specific question, but it's a general question that you will come across quite commonly. Why is the mean bond enthalpy different from the calculated bond enthalpy? And the answer is almost always the same. The mean bond enthalpy does not just consider the bond in the environment that we are looking at the moment. NH exists in ammonia, but it exists in amines and amides as well. It exists in a range of compounds and environments, and in every single case there will be a very slight difference in the value. The mean bond enthalpy considers a range of compounds and environments, and the average is worked out from there.